So we went in the lab, we did a bunch of measurements. Since we had a whole set of measurements, we were able to determine a mean, and we have a standard deviation around that mean. In other words, we've got some value, and we're saying that the real value is likely to be somewhere inside of this range. If you're noticing the way I'm tracing my pen, you're probably getting an idea of where I'm heading with this. I'm drawing up the normal distribution curve. We're saying that there's going to be some statistical likelihood that we're going to find the real value somewhere within this range. Now it could be that we just managed to get the random set of values that happen to be off from what the real value was. So what we need to be able to do is describe how sure we are that this value lies within some range. If we want to be really sure, we can widen the range that we're going to call inside of it. And because we're so sure that it's inside of this range, that means it's going to be very wide, and it's going to look like we have a very poor measurement of our value. Now, if we have a really tight range around our value, you can see that a lot of the time, we're not going to be communicating the correct range for where the real value should be based only off of our measurements. That's the idea behind the confidence interval. It gives us a range that we can say with a certain degree of confidence how likely we are to find the true value. Now you can see here that we have the equation for confidence limits. You can see that I zoomed in on that page. That way you can find this in your equations manual very easily. And you can see that we're going to use the mean plus or minus some t-value that we're going to get from a table, our standard deviation for that set of measurements, divided by the square root of n. So you can see that as we take more and more measurements, we're going to be able to tighten up the range that we have, and we're also going to end up impacting the value of t. Now we get our t-value by actually looking down further in our book at our students' t-tables values. Now notice that we have a one-sided t-table and we have a two-sided t-table. Now what we really want to be using is the two-sided under almost all circumstances, because we're saying that error is random, and so we're equally likely to be high or low. You only use the one-sided when you have very solid evidence that you're always going to be wrong in one direction. One example of that might be if you're sanding a piece of wood down and you've sanded it for 10 seconds. What's the standard deviation going to be for how far you've sanded it down for the new dimension of your piece of wood? And what's the confidence interval going to be on that dimension? Well, it's always going to be small because you're always sanding it downward. So that would be an example of a one-sided t-test or a one-sided confidence interval using a one-sided t-value. We aren't going to use those almost ever in this class. We're almost always using two-sided. You need some solid evidence to explain why you're able to use a one-sided test. So these are the confidence intervals we should be paying attention to most of the time. Now what you'll be doing is you'll be looking at your confidence interval. If you're working at a 95% confidence, the next step to do is to look along here to find your real value. Now if I scroll back over a little bit, you'll see that we're using degrees of freedom to specify this. And you saw that in one of our other videos. Degrees of freedom, for any time where you have less than something approximating the size of your population, your degrees of freedom are going to be n-1 for this. Now that's not exactly how I described it in the other video. There I gave you a much more conceptual approach. The very practical approach is if you're taking smaller sets of numbers, less than probably 100 or so, you're probably going to use degrees of freedom until you're actually describing the mean of an entire population, or until you work very hard to prove that your mean is the same as the mean of the population. So we're going to use n-1 for our degrees of freedom here. If I did 30 measurements, that means I need 29 degrees of freedom. So I come down to 29 degrees of freedom, and then as I come across, I can find the appropriate level of our confidence interval. Now, of course, for that I need to zoom out so you can see all these things at once. Here we are. So if I'm at 95% confidence interval, two-sided, and my degrees of freedom are 29, you can see that my value should be 2.045. That'll be our t-value that we put in for our confidence interval. So it'll be x bar, so average, plus or minus this times our standard deviation divided by the square root of n. So notice divided by square root of n, not degrees of freedom, it's n. So divided by square root of 30, not 29. So we go ahead and we plug that all into our equation, and out comes our number. That's how we determine our confidence interval. Now once we do that, we should always be writing our value like this. Our confidence interval might be, and I'm going to make up some numbers here, 1.045 plus or minus 0.013, perhaps. But I didn't write something really critical. Am I talking about a really small confidence interval, or am I talking about a really big confidence interval? At 95% confidence. And then the other way to represent your confidence interval would be to actually go ahead and do the subtraction where we say 1.045. If we subtract, that would be 0.032. And then we'd have 1.058. So there's two different ways we can represent that. We typically are just going to keep it in the plus minus format. Now, some people will just write their standard deviation as the plus minus. That isn't the correct way to do that at all. And it's something you need to really be aware of when you're looking at some of the journal articles and other publications that are out there, because people often get a little bit sloppy in their statistics when they don't see themselves as a statistician. And so always keep an eye on it. Often you may even want to go ahead and take the raw data and recalculate it, because sometimes when I look at the supplemental information for a journal article and I check on the reported mean and standard deviation, it turns out they're just telling me standard deviation for the plus minus. They're not actually telling me confidence interval. So always be aware of that. If they are specifying confidence interval, they always have to be specifying the at 95% confidence limit.